Hey everybody, so I wanted to show you a project I've been working on for quite some time, and kind of start with the end here. This is a port of Doom that I've made, and it's running on this FPGA board. It's a DE2i-150. It's by TerraSic. It uses the Altera Cyclone chipset. It's a really nice thing. We'll talk about it a little bit more later. But you might say, well, so who cares? There's lots of ports of Doom out there, and so what makes this particularly special or interesting in any way? And there's some truth to that, but that's where this starts getting a little bit interesting. Is that it's a port, but it's pretty much a bare metal port. This board has a Linux Atom processor side, so there's an FPGA side and there's a Linux side. But this isn't actually coming out of the Linux side. This is coming out of the FPGA environment, and what I've done is created my own machine effectively on the FPGA using a custom CPU core. And again, some of you may say, well, that's great, but how is this different? There's lots of different application systems. People have taken cores and virtualized stuff on FPGAs. What makes that so special? And that takes us to the next thing, which is I designed my own CPU core. It's a 32-bit CPU with a variety of features, which I'll probably talk about in future videos. And then around that CPU core, I've implemented IP blocks for SDRAM, a VGA interface, a real-time clock, SPI interfaces, serial interfaces, and whatnot, so that effectively this joystick in Doom is mapped for the arrow keys. So if I go like this, it's up arrow and down arrow and whatnot. And because I don't have a keyboard enabled for this system, these are some of the other buttons, like the fire button and whatnot. So I can actually go and use that joystick and drive around. Now you'll notice it's kind of slow, and that's because my CPU core doesn't have really any optimizations whatsoever in place yet. I'm going to be looking at that as kind of a next phase, but it's not pipelined. It's a single core. It has no cache. It's running pretty much as simple as you can get. Now, here's the serial output of the system. It's just a bunch of debug content from Doom. But one of the reasons I was able to make this port and do it relatively painlessly, because I ported most of this in less than 2 weeks, 2 or maybe 3 weeks. And most of that time was actually finding and fixing a bug in the CPU core that this code kind of exhibited. And what's interesting and what made it so straightforward is that I've built the GCC, binutils, and most importantly, newlib stack to cross-compile and cross-assemble to my core. And what that's allowed me to do is things like where you would have in the Doom code, like the open system call or fopen or something like that, newlib would actually has support for all of those things. And then I have system call stubs, which go and actually map to the FATFS library, which then I've implemented to hook into the SPI interface that I designed on the board here, and then ultimately talk to the SD card. So if I interrupt Doom, it goes to a basic monitor program, and if I hit this key, C, it does a directory listing. And so it's doing a directory listing based on what is, and it's not focusing well, but it does a directory listing based on the information that's on the SD card. And all of these files are ELF binaries. They're the binutils and GCC compile and link and create static executables that are in ELF format that this system recognizes. And so then all I need to do is copy the binaries onto an SD card and slap it into the machine, and I can run them. So, you know, there's a bunch of different programs that I can run. One example is a demo program for this LED matrix, and you move the joystick around and it moves. Well, there's a little bit of an issue here with the cabling, but moves around the cursor here. So basically that's, yeah, there's a cabling issue there. So it can move around the screen and whatever. So that's it in a nutshell. The machine itself has cores that support the onboard VGA, static RAM. I wrote an SDRAM controller. It's got an LCD interface. It has a GPIO for several of the switches and the buttons. SPI that talks to the micro SD card. The A to D SPI interface that this joystick is connected to. I wrote a frame buffer and driver for this RGB LED interface. Real-time clock is SPI based, and this is an SPI touchscreen and LCD panel. So those are some of the other little bits. And like I said, the CPU core is really unoptimized at this point. The only thing that I kind of threw in there for some performance boost is I implemented a single precision floating point so that the libc system doesn't have to emulate that in software. So doubles, it has to actually do in memory using integer operations, but single precision floating point is actually done native in hardware. The interesting thing about Doom, just as a random comment, is that it uses fixed point 16.16 numbers in its computation. So all of the rendering is integer math, because back in the day that's pretty much all you had to work with. So this is definitely a work in progress, but it's been really a neat process so far. Just a quick example of the little LCD test there. And I'm going to continue to work on it. Part of my interest in getting Doom going is that I want to work on different optimizations, and I want to see the impact of them. So one of the things I can do is see, for example, if I add a cache for the instructions, or even just for a general memory cache, how much of an acceleration does that have with the frame rewrites? Would pipelining memory operations be better even than a cache? Or, you know, obviously continuing to add both of them together would be a good thing as well. So those are all future projects I'm going to be working on. So stay tuned. Hopefully this was interesting, and you know, you'll hear more about it later. Thanks.